Alright, so now I'm going to move on to modules 8 and 9 as we prepare for our exam. I think there's 4 different probability distribution functions you guys learned in module 8, and then you guys talked about the Poisson probability distribution function in module 9. Now, the main trick to this is going to be recognizing which distribution function you should be using. That is the point of these examples, and you should feel comfortable about that as you walk into the exam. I am going to pull open my formula sheet, because you guys do have a formula sheet that'll be provided at the end of the exam. And sometimes looking at this formula sheet can also be helpful in determining which distribution you're talking about or you're dealing with. So there's the 4 distributions, 1, 2, 3, 4, and then Poisson for module 9. You will also be given a Poisson table on the exam, and you will be given a binomial table on the exam. So let me have those all open. All right. So now let's go ahead and read through this first example. A rental company manages 3 homes, 5 apartments, and 7 townhomes. I like to draw little visuals as I'm doing this. So 3H, 5A, okay, and 7T. Right? The rental company wants to randomly select 5 properties to participate in a survey, and they'll be selected without replacement. Okay, so basically this is their population, and they want to select from this. They want to select 5 to get their sample. So their sample will be 5 properties. So this is, since you have 3 different types of things, you have 3 different types of objects, this is a multivariate. Now, it's multivariate, hypergeometric, right? It's not multinomial. So let me go to my exam formula sheet. So this is the multinomial probability distribution function. It's not this one because we are sampling without replacement. So that's why it's not this one. If you were sampling with replacement, then you could use this, right? But because it's without replacement, it's not this. Rather, it is the multivariate hypergeometric because we are sampling without replacement. Now, you know it's multivariate because we have 3 different types of objects. We have homes, apartments, and townhomes. So you see these 2 are the only 2 options with multivariables, or more than one variable, right? Okay. So the first question is, find the probability that there will be exactly 1 home, so H equals 1, 2 apartments, so A equals 2, and 2 townhomes, T equals 2. Okay, so using the multivariate hypergeometric probability distribution function, we can solve this. So let me go and write down that function. I'm going to write it down here so that way I don't need to look back and forth. So I'll use x, x1, x2, x3. So h is x1, a is x2, t is x3. Okay. This is n1, choose x1, n2, choose x2, n3, choose x3. All divided by n, choose little n. Okay. So let's use it. In this case, n1, the number of homes, is 5, and we are choosing one of them, right? The number of apartments is, how many apartments? Oh, sorry. Number of homes, how many homes do we have? 3, sorry. 3 homes. Let me erase that. So n1 is 3. Alright, the number of apartments is 5. There's 5 apartments. And we are choosing 2 apartments. Okay, and the number of townhomes is 7. 7 townhomes. And we are choosing 2 of them. All divided by capital N, which is a total number of properties that they manage. So they manage, let's see, 15 different properties. So that's 3 plus 5 plus 7 is 15. And little n is our sample size, 15, choose 5. Okay. Now, we calculated probabilities like this in earlier modules, and the topics covered in module in the first exam. So, this the multivariate hypergeometric distribution, you don't actually even need to use this formula. This formula is really it's to help, but like you can also just use the tools that we learned from previous modules, to go straight from here to there, right? Okay, so let's see. The next question says, what is the probability that at most one home will be randomly selected to participate? So what's important here to notice is that this says something about a home being selected, but it doesn't say anything about townhouses or apartments, so they're kind of grouped together as one other group, okay? So there's homes and there's others, all right? Because of that, there's only two options. There's home and other. That changes this from being multivariate to being just a single variate hypergeometric probability. Okay, so let me write this down. So we're talking what's the probability that there is at most one home. So the number of homes, H, is less than or equal to 1. At most one home. So that means that they either have 0 homes selected, or there is 1 home selected. Okay, so you can add these two probabilities. So this is a single variate hypergeometric probability distribution because there's homes and then there's others, right? Right, so let's see. How many homes are there? There are 3 homes. So we're doing 3, choose 0. How many others are there? There's 5 plus 7 different types of housings or different types of properties. So there's 12, and you need to choose 5 total, so that needs to be 5. All divided by 15, choose 5. 3 choose 0 is just 1, so you could just write 1 there if you want to, or just not write it at all. Okay, and then plus 3 choose 1 home, 12 choose 4, right, the leftovers. All divided by 15, choose 5. All right, so this was multivariate hypergeometric, and this is single variable hypergeometric. All right, so the next question is to calculate the variance for the number of homes that are selected to participate. So this is basically calculate the variance for a hypergeometric probability distribution. You should know how to do that. So we need to calculate the variance. Actually, you know what? I'm going to start with the expected value. How do we calculate the expected value? You need to know these two formulas. N times P, and the variance will be N minus little n, n minus 1, npq. Okay? So this is the expected value and variance of a hypergeometric random variable. All right? Okay, so let's start with what is n? What is n? N is our sample size. In this case, it's 5. We're sampling 5 properties. What's p? The probability of getting a home. So 3 out of 15. So 5 times 3 out of 15 is 15 over 15, which is 1, right? What's important is that this did come out to a whole number. The expected number of homes is 1 home. But if it came out to a decimal, like say 1.3 or something, you don't round that off, right? This is the average number of homes that get selected. So it can be a decimal. All right. For variance, capital N is the total number of properties that they manage. Little n is the amount that you're sampling. Capital N minus 1. Little n P is 3 out of 15, and Q is 1 minus P, 12 out of 15. All right, and I'll leave this. You can go ahead and multiply this across, right? So 10 over 14 times 5 times 3 over 15 times 12 over 15. So you can calculate that. All right, so this is an example of the hypergeometric probability distribution function and the multivariate hypergeometric probability distribution function. Okay, so now let's move on. Very similar type question, guys. Okay, so I didn't change the question on purpose because I want us to notice the difference between these two, right? So hypergeometric versus what I have going on here is a multinomial and a binomial. Okay, so rental company owns homes, apartments, and townhouses. 70% of their properties are homes, 10% are apartments, and 20% are townhomes. Rental company decides that they want to randomly select 5 properties to participate in the study. Now, they don't say anything about the total number of properties that they have, so we would assume that that's a large number of properties, right? They don't say anything. They also don't say anything about sampling without replacement, so assume that they're sampling with replacement here, right? So because they have just told us these percentages, and we're sampling 5, we're selecting 5 with replacement, right? Or their population is so big that even if it is without replacement, that that there's chance of selecting the same person twice is just minuscule. Or same property twice is just really small. So this is an example of a binomial or multinomial probability distribution. Now, right now it's multinomial because we have three different groupings here. So the first question was probability of getting exactly 1 home, 1 apartment, and 2 townhomes. So home equals 1, apartment equals 2, and townhome equals 2. What you'd want to do is you need to find, so you're going to use your multinomial probability distribution function. You're going to use this one, okay? So this is going to equal n factorial over p, I'll use subscript h, x subscript h, I'll use that guy, factorial, x subscript a, factorial x subscript t, factorial times p h to the x h, p a to the x a, and p t to the x t. Okay, so this is straight from the formula sheet, basically. So what is n? N is your sample size, right? So we're selecting 5 properties. So 5 factorial divided by, what's this? This is 1. We have 1 home that we're selecting, 2 apartments that we're selecting, and 2 townhomes that we're selecting. What's the probability of getting a home? Well, they own 70% of their properties are homes. So that would be 0.7 raised to the power of 1, right? The number of homes that we're trying to find the probability for. Okay, 10% are apartments, so 0.1 to the power of 2 times 0.2 to the power of 2. Okay, so you plug this into your calculator and you can solve this. I'll leave it here. You can finish this on your own. Now, what's the probability that at most 1 home will be randomly selected? So again, now we have changed this from a problem involving all 3 different types of properties to now just being home versus other. Okay, so this is multivariable, and this is only one variable. So this is the binomial. Binomial only has 1 variable. Okay, so then from multinomial to now this is just home. Okay, so at most 1 home. So I'll let, say, x be the number of homes that are selected. Okay, so at most 1, so x is greater than or equal to 1. All right. So if we could find the probability, not greater than, let me read it. At most one home would be less than or equal to 1. Yeah. At most one home, right? Less than or equal to 1. So x equals 1 plus the probability that x equals 0. Right? So either one home is selected or 0 homes are selected. All right, so we could use the formula and choose x. So in this case, n is the sample size, which is 5. X is, if I'm doing for one home, x is just 1. The probability of getting a home is 0.7, brought to the power of x, which is just 1. Q, which is 1 minus p, 0.3, and then brought to the power of 5 minus 1, which is 4. Okay, then for 0, 5 to 0, 0.7 brought to the 0 power, 0.3 brought to the 5th power. All right, you can calculate this. Another option is whenever you have binomial, you do have a binomial table. So you should always think to yourself, can I use the binomial table? Once you recognize that you're in a binomial situation, can I use the binomial table? So be careful when you're using the binomial table because it is a CDF table, meaning it's the sum. So when you're reading it, it's the sum that you're less than. So, oh good, that is what I want. I want to know basically the value of f of 1, right? By definition, that's what CDFs are, less than or equal to, right? So if I have this, okay, my n is 5. Okay, so that's good. My r, in this case, is 1, because I'm doing f of 1. All right, got that. P is 0.7. All right, so let's see. 0.7 is right here. There we go. Okay, so here it is, 0.0308. Okay, 0.0308. If you calculate this, you should get the same answer. But it's important that you know how to use the binomial table in addition to knowing how to use the formula, because in the exam, it's very likely that it will be much more difficult to use the formula, right? That you have to add up a ton of different probabilities. So it might be probability x is less than 15 and r is 20 or something like that. Something ridiculous where they're just, if you were to sit there and use the formula, it would take you forever. But if you were to use the table, you would just, go directly, to the appropriate n and r. So if you were at 15 and 20, then you just go here, right? 0.7. You would just go straight to here. So much easier than having to calculate all the different values from 0 to 15. Okay? You should definitely know how to do it both ways. Most likely your exam will have a question with binomial where one you can use the formula or can use the table, and the other one you cannot use the table. And you'll know you can't use the table because p will be some value that's not one of these p's, or n will be larger than 20, right? So you can't use the table because you don't have any values that are beyond that. Okay? All right. So now how to do it both ways. Moving on. Last example from modules 8 and 9. This example is coming from module 9. Oh wait, before I move on, actually, in the binomial, I didn't do part C, find the variance. So finding the variance for binomial, you need to know how to do this, the variance and the expected value for binomial. You need to know these formulas, n times p, n, p, q. Okay, so you should be able to calculate the expected number of homes that you would select. So we have 5 that we're selecting. Probability of getting a home is 0.7, so 5 times 0.7, that's the expected number of homes. So 5 times 0.7 is 3.5. Again, you don't round that to a whole number. You leave it like that because that's on average. You would select 3.5 homes. Okay. NPQ, this is the variance. So this is 1.05. Right, these equations for variance and expected value are not on the formula sheet, so they are equations that you need to memorize. All right. Okay. So moving on to the last example. For Module 9, we have the Poisson distribution. Now, Poisson distribution is really great because you will always immediately recognize it's a Poisson because it'll say something like it follows a Poisson process, right? Or they'll specifically say this is Poisson, so there should be no debate about that. You'll see, oh, okay, it's Poisson. That's what's happening. Usually, all Poisson examples are like you're kind of counting events as they come in, right? So in this case, we have changes to airport procedure require considerable planning. This example was taken from one of the handouts, so you might recognize it. It's one of the supplemental handout questions, but I've changed it a little bit. So suppose small aircraft arrive at a certain airport according to a Poisson process. So there it is. That tells you, oh, it's Poisson. At the rate of 6 per hour. What is the probability that exactly 4 small aircraft arrive in a 1 hour period? Okay, so it's 6 per 1 hour, right? I think a great idea whenever you're doing Poisson is always write what your ratio is over to the side. So 6 aircraft per 1 hour, okay? So this will be mu, all right? So what is the so starting with part A, what's the probability that x equals 4? Now, we do have a Poisson table, so let's go to our Poisson table. Let's see if we can use it. So let's see, what do we have here? So R, what is R, right? R is, so this is a CDF, right? So we're summing. These are not PDF values, these are CDF values, okay? So it's a sum from 0 to R, okay? And then these are all the different values of mu. Let's see, what's our value of mu again? It's 6, so 6 over 1. So what is 6? Let's see, right here. All right, we want to know 4. Is that the answer right there, 0.2851? No, that's not the answer, right? Because that's the probability that x is less than or equal to 4. So actually, let me go ahead and move this over. So could I use the table? If I really wanted to, I could. This is equal to the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 3. Right? If I subtract off, so if there's 5, 4, 3, 2, 1, right? So it goes on upwards in 0. If I have less than or equal to 4 and I subtract less than or equal to 3, then I'm left with 4, right? So that's what I want. So if I look at my table at the 4 value, what do I have? 0.2851. 2851. At the 3, when R is 3, what do I have? 0.5 or 0.1512. All right, let's go ahead and do that subtraction. 0.2851 minus 0.1512. Okay, and this is 0.1339. Now, I could have also used my formula sheet. For this question, I could have also used my formula sheet and just used this Poisson distribution equation right here. So had I done that, okay, this is equal to mu to the x e to the negative mu divided by x factorial. Mu is 6, x is 4 right now. E to the negative 6 divided by 4 factorial. Okay, if you do this, I'm going to just go ahead and do it in my calculator real fast. You should get the same exact answer as the table gave you. Okay, let's see. So I have, when I did this, I have 1, 3, 3, 8, 5, 2, 6, 1, 8, right? So if you were to round that to 4 decimal places, you get the same thing. Okay? Okay. You should know how to do it both ways. I just want to point this out because I could have a mu that's not one of these mu's, right? So what if 6.25 airplanes landed, right, per hour? Well, then you have to use the equation. You are not allowed to use the table because the table doesn't have that value for mu. So you need to know how to do this question both ways. All right, what's the probability that exactly 40 small aircraft arrive in a 8-hour period? Okay, so now 8-hour period, this is going to change mu. So it's 6 aircraft in 1 hour. So now we want to find a new mu for 8 hours. Well, multiply both sides by 8, and you get 6 times 8 is 48. 48 aircraft in 8 hours. Okay? So this is my new mu. So 48 is mu. Oops. So B, what does it say? It says that at least 4 arrive. At least 4. So that means X is greater than or equal to 4. Now mu here is 48. So I'm not going to be able to use my table, I don't think. So if I go to my table, the highest value of mu that I have on my table is 18. So I'm not going to be able to use the table. So at least 4. You are, however, going to need to flip this around because we can't go x equals 4 plus x equals 5, x equals 6, x equals 7, because it would just continue on forever, right? There's no upper limit for the number of aircraft that can land there, but there's a lower limit of 0, right? So let's use the complements. That is less than or equal to 3 or less than 4, right? So this is the complement, 1 minus the complement, okay? So then we would need to 1 minus the probability, x equals 3, minus the probability, x equals 2, minus the probability, x equals 1, and minus the probability that x equals 0, okay? So now I would need to use my formula, 1, 2, 3, 4. I need to use it 4 different times, and I need to solve this. So 1 minus 48 to the third power e to the negative 48 divided by 3 factorial. Okay, and I'll leave this for you guys to solve. So if you have any questions about solving it, you can post that on the discussion board, or if you just want to check that you have the right answer, also very happy to check that for you on the discussion board. What's 0 factorial, by the way? 1, right? So when I divide this by 0 factorial, it's just 1. So I didn't write it right there. Also, 48 to the 0 power is also 1. Okay? Let's see. Okay, part C. What's the oh, actually, I have 2 part B's. So let me change that to part C. Let's change this to part D. So what's the probability that at least 4 arrive in a 1 hour period? So 1 hour, again, now we're back to mu being equal to 6. Okay. Let's go here. Let me go down here. So now mu equals 6 because we're back to the 1 hour period, but it still says at least 4, right? Oh, you know what? I realize this says exactly 40. Yeah, I was mixing up because they're both lettered B. I'm sorry about that. So exactly 40 is a lot easier than this, though, isn't it? Because we just do equals 40, and then this equals 40. Okay, and then we just need to use our equation once. That makes a lot more sense. That's a lot easier to solve. on the exam, if you run into, so in this case, try plugging this into your calculator right now, actually. So, what do I have? This is to the power of 40, e to the 48, 40 factorial. If you plug this into your calculator and you get an overflow error, the reason why you're getting that is because you have these really big numbers, like 48 to the 40th power. And that's okay. So if you end up having that problem during the exam, just circle your answer without it being simplified. It's okay. Okay? Okay, so now at least 4 in 1 hour period. Okay, so let's do that one. So back to mu equaling 6. At least 4 greater than equal to 4. Hey, well this one's going to be that's going to be a lot easier than the way I was doing it before, because now we are able to use our table, so we don't need to calculate it, 3 times in a row like that. So this is just f at 3, and 6 is on my table, so let me pull up my table. Mu equals 6 is on my table, and f of 3, so that's 0.1512. So it's just 1 minus 1512. Okay. All right. Last part was D. Find the expected number of aircraft to arrive during a 10-hour period. All right, so this is basically just asking you to, so we have how many in 10 hours, right? So there's 6 per 1 hour. So now let's just change this to 10 hours. How many come in 10 hours? Okay, so just solve this for mu, and you find that 60 come in 10 hours. So what's mu? Mu is 60. So the expected number of aircraft, mu is 60 aircraft per 10 hours. So mu is 60. Okay, and the mean, again, it doesn't have to be the expected number of aircraft that are landing. It could be a decimal, right? Don't be upset or worried if you find that, because that is just the expected number is just the average number of aircraft that are coming per 10 hours.